Thank you so much for the invitation and for being here for my talk. It's been a fun conference and I've learned a lot of new things. So I'm going to tell you about weighted error theory, joint work with Jesus de Loera, Nathan Kaplan, and Cheng-Yang Wang. But a lot of it is going to be motivation because we believe this is like a viewpoint that can benefit people who study functions in algebraic combinatorics. So hopefully we can convince you to use our tool for that. So let me start with sure functions. And so just to introduce some notation, I'm gonna let this be the set of semi-standard Young tableau of shape lambda with entries in D. And well, as we know, then the sure function is going to be, I guess, let me give because I wanted to say the indices for a reason. Okay, so that's the definition of the sure function that we've seen. I mean, we've seen it a lot. Mostly we've seen it in the determinantal form, but this is equivalent. And so I had an example here for this partition. And so here we have the sure function with the corresponding semi-standard Young tableau. And so remember, this means semi-standard means you want to be weakly increasing across rows and strictly increasing along columns. Okay, and so, well, we have then that the Kostka number So as you see here, I combine these two together. So if I combine equivalents, so different Young tableaus can give us the same monomials. So if I combine monomials into one and look at what the coefficients are, those are going to be given by the Kostka numbers. Yeah, with content alpha. So what I mean by that is, so here, if we look at this one, we want to see how many semi-standard Young tableaus, so among this that I have listed here, how many have content 1, 1, 1, meaning that you only see 1, 1, 1, 2, and 1, 3. So in other words, the ones corresponding to this monomial. So you're going to have 2. And then for all the other ones, you're going to have 1. Okay, so then we're going to have, so the whole point, so eventually we will get to our Hart theory, but if you're familiar with it, there's going to be polytopes that are going to appear and be central to this talk. So let me get ahead and tell you something about polytopes. So if we look at the Gelfand Tsetlin polytopes, okay, so the Gelfand Tsetlin polytope, GT, lambda comma mu. And there's different versions of it. So I'm giving it with 2 parameters. So I'm intersecting the Gelfand Tsetlin cone with 2 conditions, one for lambda and one for mu. And this is going to be a pair of partitions. This is going to be given by the following inequalities. So first, you want all entries to be greater than or equal to 0. Second, you want that, well, I'll skip this one because second, this is condition number 2. You want, I guess this is 2 and 3. Okay, 3 is the one along on the outer diagonal. So here, I want these equalities to hold. 2 is, well, you see up, like as you go in the zigzag, you want to be always increasing. And then the last condition is that, okay, so x1, x11 is going to be, yeah, this is okay. Is that okay? Oh, wait, sorry. No, I don't want it there. Oh, no, I prepared my picture ahead of time, and now I'm, okay, red, but it's okay. It's at the bottom, yeah. Okay, so this is condition number 3. And condition number 4 is that I want this to be mu and 1, and then for, well, I guess I could have written in one go. Wait, I'm doing it too quickly. Okay, now I'm okay. Okay, so it's easier in the picture, but okay, so this one is easy. This should be mu1. And then if you look at the sum of these two, this should equal mu2 plus mu1, and so on and so forth until the bottom. Okay, so if you consider all those 4 inequalities, you're going to get a Gelfand-Tsetlin polytope. And so what does this have to do with the Kostka numbers? Well, it's very well known that for any pair of partitions, we have that the Kostka number is equal to the number of lattice points I'll just say n because I won't always, it lives in some space. So just that space, I could have written that, but it's okay. This is equal to the Kostka number. Okay? And so if we wanted to see it in action in a very small example, so we can look at this example that we saw over here. And so there we're just going to have a very small picture. We're going to have 1, x12, x22, 2, 1, 0. And we want that the sum of these two should be equal to 2. And so the way our inequalities work, you see there's going to be 2 solutions. So the Gelfand-Tsetlin, for our running example, for this particular example, is going to be this line segment. Okay? And there's 2 lattice points in that line segment. Okay, so this is, I'm gonna jump a little bit, but so first, well, I'll stick with sure functions for another polytopal story, but in terms of, like, I wanna pause to emphasize that Kostka numbers can be computed using polytopal methods. Okay. So that's not the only thing that you can compute. Well, I'm not sure if it's fair to use polytopal methods, but a polytope lets you interpret a story very beautifully. So if you have the following question, no, I can do it with mu or alpha, doesn't matter. Okay, so this is a question that is of interest, and I mean, it's very broad, so whatever you can say, it's probably very hard to say, but it would be of interest. So I want to talk about a theorem so this paper was mentioned yesterday. Okay, so they show that they show log concavity of these coefficients. So they show that for all pairs of partitions, and different from J, you have that So you have log concavity when you vary your mu in special directions. And so I like drawing a picture of this because then, we've seen this has to do with the coefficients of the Schur polynomial. So if you look at the Newton polytope of, let's do it for our example. Then, well, in general, this is always, you act on by the permutations on the entries of this vector. So you're going to get what is maybe a weight polytope or a generalized permutahedron of some sort. But in this case, you just get a hexagon. I'll highlight the lattice points. Okay, so those are the lattice points of the Newton polytope of that Schur polynomial. And so what they're telling you, so if I decorate this with the coefficients, so each of these lattice points correspond to a monomial in my Schur, so I can decorate it with the coefficient that accompanies that monomial. Then what they're telling you is that as you go along like these lines, these three special directions, you're going to have log concavity. And then this is a very small picture, it's very silly, but it holds in general. Okay, so, and of course they prove it with better techniques. But having this polytopal perspective really convinces you that, looking at these directions is not like something completely arbitrary, but it makes sense in the context of this polytope. No, because, yeah, no, I'm thinking of that. Okay, so the next one I want to talk about RSK correspondence. And maybe I should say a downgraded one, because of course, well, we know that this gives a bijection between, well, we've seen it before, but, well, yeah. Well, yeah, I'll write it like this, it's okay. So this should be a Young tableau of the same shape. But the number of entries, or the type of entries you put in them can vary. That's no issue. And it's a bijection with matrices. Okay, and it's a beautiful bijection, very studied. I hope everyone who's taking a graduate combinatorics course has learned about it, very well known. But the point is that if P has content mu and Q has content nu, then you have that, well, the corresponding matrix is going to have row sums equal to mu. So this is a vector. So the sums of the first row are going to be the first entry of this partition, and so on and so forth. And then the column sums are going to be mu. Okay? And so there is a polytopal view that is going to be a little bit of a downgrade because it's not exactly a bijection. It's not going to tell you how to correspond. I'm going to give you a polytope on this side, a polytope on that side, and the count is going to agree, but it's not going to tell you exactly how to correspond the lattice points. For that, you would use this type of bijection. But the polytopal view is as follows. So, well, we have that the set of partitions of n is the same as, I'm going to call it P, is the same, is the set of the lattice points. And, okay, I guess that one I can call n. That one's little n, that's okay. is a set of lattice points in a polytope where this is a very simple polytope. It's a simplex. Okay, so this is nothing. Yeah, of course, I just wrote down the conditions to be a partition. Okay, so here, this is our first polytope that we have. And now we're going to fix a pair of, because I'm going to look at this bijection after fixing these two mu and nu. So we're going to fix mu and nu, and we're going to consider a function that is given by W of lambda. So if you have a lattice point in that polytope, it's going to be equal to the product of these two Kostka numbers. Okay? And so in this case,
the same twice?
Oh, sorry, not.
Oh, okay.
Sorry, thank you. And so this, from what we've said over there, that this number is equal to this count of lattice points, this is also a count of lattice points. And I'll just put an end there. Okay, so as a consequence of RSK, implies that if you look at this sum, so this bijection implies that the count is going to be the same. But I'm rewriting it in a polytopal point of view because that's going to appear for us when we talk about weighted Erhard theory. So this function I introduced, I'm just rewriting it like this. So this is actually a sum over the lattice points of a polytope, where each lattice point you weighted it by something. Okay? And so this is going to be equal to, on the other end, the number of lattice points of a polytope. Okay. Uppercase M. So this is the number of lattice points in another polytope, where so if you look at what the image is of such a tableau, you're going to get a polytope here. It's going to be a transportation polytope. Oh, sorry. But I mean, it's just, yeah. So it's not, well, it is a fancy polytope because transportation polytopes are fancy, but the definition of the polytope is not fancy. You just want. Okay, so this is not RSK because, as I said, I'm kind of corresponding like objects here with lattice points in here, but I'm not telling you exactly how. But it is a consequence, and it's a nice polytopal view. And this is a cool formula. Okay. And so this type of formulas, let me say, this is going to be kind of like the focus of what I want to tell you, or like going to lead to what our main theorem is going to be. So weighted equals just a classical lattice point sum. So, and this appears in other contexts, just to be brief. So like, let me see. Let me just, okay. I'll be quick here, because it's not that important. But this type of story also appears in the theory of Newton-concave bodies. And so in this context, you often care about the following question. So given a variety, a projective variety, is there a polytope such that the toric variety for delta, that I'll denote by x sub delta, approximates, so I won't be precise here, approximates your original variety, right? So toric varieties, you have many tools to study them. This, like, the polytope tells you everything about your toric variety. So being able to approximate general varieties by toric varieties is desirable because you have more tools to study them. And so in the context of spherical varieties, so this has been answered in many instances, but it's not, there's never like an answer that works for all varieties, that it doesn't come with some kinks. So answering this question is important in general. But so for spherical varieties, there's a nice answer. So if you have G, a connected reductive algebraic group, you have it acting on a projective variety where your variety should be normal. And what you want for it to be spherical, you want that there exists, you want that B, that the Borel subgroup in your G has a dense open orbit. Okay, so that's very briefly what a spherical variety is. So for those, Okunkov and Alexev and Brion, two separate papers, they introduced, so for these ones, the answer is yes. Okay, so Okunkov. So they introduce a polytope, delta of x, that accomplishes this, okay? And so one way in which it approximates your variety, there's a toric degeneration, if you know about that, but also like tying up, we heard about Hilbert functions. So the Hilbert function for this toric variety is the same as the Hilbert function for this projective toric variety. So you can think about some numerical invariance being preserved between the two varieties.
Can you give an example of a spherical variety? Is there?
Yeah, I'll give one in a minute. Well, kind of. Because for the flag variety, so the flag variety fits into here, but for the flag variety, you just get a Gelfand Tsetlin polytope. I mean, it's good, you know, but what I will tell you now about these polytopes is not that very interesting for the flag variety. But yeah, for if X is a flag variety, this is a Gelfand Tsetlin polytope. Same, like for Grassmannians, you get other types of Gelfand Tsetlins. Okay, so here, yeah, so for GLN, it can be a little bit more precise, but not super precise. You're going to have a projection where, like it depends on your variety, but for the flag variety, this is going to be a point. That's why it's not super interesting. And this is a Gelfand Tsetlin. But this is what is called the moment polytope. So this, I won't be too precise here because I just want to kind of connect it to this idea and to other idea that will appear later. So yeah, this is going to be a bit abstract, and I apologize for that. I won't tell you what this is. This is that polytope. But what I do want to emphasize is that the fiber are Gelfand Tsetlin polytopes. So you can imagine that down here you have your P of X, and then, well, the fibers where X is a lattice point. So I'm only highlighting the lattice points of your moment polytope, and on top of them, you're going to have different Gelfand Tsetlin polytopes. I mean, different lambdas. Okay, so, and this picture will, like, you should remember this picture because it will play a role in like, I'll highlight it because this and that will show up in our theorem. Okay. Okay, and just one last thing that maybe is not as connected to weighted in her theory, but maybe polytopes are rising in the study of this type of functions, is like there's a poster outside by Greta's student, Xiao, that talks about how you can use polytopal tools to give conditions of positivity on Kronecker coefficients. So connecting this type of numbers to polytopes can be very, very productive. So if you want to know more about a different direction, you can go and look at the poster.
Sorry, can I just ask, because I'm not sure I understood. So delta of x is that's the data for the toric variety, yeah?
Yes, it's for the toric variety, yeah.
So what is p of x, the moment polytope for which?
Yeah, so this is the moment polytope for G acting on your spherical variety. And as I said, if you take this to be the flag variety and this to be GLN, it will happen that it's just a point. So for more interesting varieties, you have to work harder to get them. Because moment polytopes are easy if this is a torus, but if you have more arbitrary group actions, they're not that easy to describe. Well, concretely, I mean, there are descriptions for them, but not very concrete. Okay, so now let me talk about classical Erhard theory. So there's this theorem by Erhard, and he has a very interesting life story that gives everyone hope if they think they're too old to make contributions in math. Look at his biography. And it says, so if you have a polytope P with all vertices in C to the n, so this is what is called a lattice polytope, then this function is a polynomial. Okay? So what you do is you start with your polytope, you blow it up, you're expanded by scalar multiples of itself, and for each scalar multiple, you see how many lattice points you have, and that's going to give you a polynomial as long as all vertices are in Z to the n. Now, if you have a rational one, meaning now, if they're all rational, then you don't get you get what it's called quasi-polynomial. Okay, so it's still just a collection of polynomials, so it's still very well structured. So maybe what is best is to look at an example. So if you have this to be your polytope, where you have your vertices are 0, 0, 1 half 0, and 0, 1 half, then you're going to have that this lattice point count is going to be, yeah, the precise numbers don't matter much, but okay. So you're going to have that it's a quasi-polynomial. So you have two polynomials. It's always going to be a finite list of polynomials. It's very well structured in the sense that how you evaluate will depend on the period, or you take this modulo some number. The period is always going to be related to the least common multiple of the denominators. And so this is an example of what happens. It could be that you could have vertices in Q to the n and it's still a polynomial, but this is the best the theorem can do in general. And if you have real numbers as your vertices, then you can get anything, I think. There's no good theorem for that. Oh, and I want to leave this there. I mean, we can remember it came from the Kostka numbers, but I want to leave it there because we're going to have it. Okay. So let me write it over here. We can note that, another way to write this, this is, okay, this is just, because I'm going to vary this. I'm going to vary this 1. So this function I just did is just when you add 1, for each lattice point, you just add it once. Compare it to here where we actually weighted each lattice point. So for the weighted Earhart theory, then we're going to consider functions of this form. I guess, I know, well, yeah, I'll just put them evaluated to 0. Yes, if they can evaluate to other places, but probably because of lattice theory, this is the only interesting case. Okay, so we're extending, rather than just having W be 1, we're allowing arbitrary W's. So a quick example. A very small one, because these ones can be hard to compute. So if you just have this very simple line interval, and that's your weight function, then what you're going to get well, yeah, calculus students know the answer to this, right? So you just get it. Okay. Okay, but I'm not going to allow arbitrary, because like the way I wrote it down, this could be like a function. It's the same as choosing at every lattice point of your polytope a different number at random, right? That's not going to work ever. You'll never have structure like that. So our setup, further, we're going to restrict the type of W's that we want. We're going to consider W of X be so this is a function from Z to the N, where my polytope, here I guess I should say P lives in R to the N. Okay, and Q is a polytope. So for each lattice point on your polytope, you're going to have a different Q, and this is going to be given by okay, so it's like a continuous family of polytopes in some sense.
Okay. So I'm a bit confused between M and N.
Uh-huh.
So Y does not live in Rn?
No. So because going back to this picture, you can imagine, okay, so the way I drew it, let's say this lives in R2. Here I can put whatever polytope I want. So all of this, I forget that these are Gelfand Tsetlin, but these ones could all live in R1 if I wanted to, you know? Yeah, I have freedom to choose the dimension of your polytope. Well, no, once you have your polytope, I have freedom to choose the dimension of the polytopes that you put on top of each lattice point.
And then what is R doing there?
Oh, some R.
No, but then...
Right? Can it be any R?
No, xi's are n vectors, right? So n has to be...
No, yeah, because I don't... This is like how many equations you have to define your polytope, and you can define it without as many equations as you want. Well, up to like, I don't know, it should be a polytope or something, but yeah. R is free.
Right. D's and E's are you can choose.
Yeah, these are fixed. This is fixed. Yeah.
C's and D's are fixed.
Yes.
And so then this is asking basically for the number of positive integer solutions of an linear equation.
Yeah.
Okay.
This part, yeah.
It's not positive integer solution.
But, oh, they don't have to be positive, yeah. So this is asking a number of solutions.
The y has to be non-negative.
Yeah.
Yeah. Yeah. Yeah, you're right. Yeah. And I would say, okay, this is just so we can write the proof of our theorem. We need it to be in some form, like we need to choose how to write our polytopes in some way. And when you're choosing to write it as an intersection of half spaces, it's, well, I guess in this case, yeah, it's easy just to choose one form. So, so this is like, we can get many types of polytopes.
So, but it's not just that the weight is a point count in a different polytope, it's something more specific to that.
It is like, so as I said over here, so you can hear, so here you have your
I'm
x.
hard to understand if this is a picture of that.
Yeah, exactly. This is a picture of that. So here we had Gelfand Tsetlin polytopes, but I erased that, so that was in the past. But now, for each x, when I evaluate it, if I look at how many lattice points this Q has, that's exactly the weight that I assigned to this W. Okay. So yeah, let me tell you our theorem. Okay, so let P be rational. So that means that all the vertices are in Q. And WB as above. Then we have two things. First, that we construct a rational polytope P star, R to the n plus m, such that classical equals weighted. Oh, let me do it at level 1. Yeah. Okay, so I could put a 1. I don't know if it's good to put a 1 there or not, but anyways. Okay. The weighted theory for this one agrees with the classical for the other one. Okay. And then I didn't do it for T in general. Oh, sorry. No, TT, sorry. 1, 1, 1, 1. The number of lattice points of this one agrees with the number of, like what we have over here. Okay. The second one, now of course, when you're doing Ehrhart theory, you want to vary the T. And if you want to vary the T, then you need your W to be homogeneous. So you need your E to be 0. So if E is 0, then you have that. Like, right, our construction, when like, we can factor out the T from our construction. And now I can write this formula for general W's, for general T's. Okay.
Should that be a T to the n for every?
Here, no.
I mean, when you scale for each dimension, you'll pick up.
No, but here I'm not scaling. No, yes, I am scaling. But the way, I guess I didn't write the polytope, but no, I mean.
Is already on each dimension.
Yeah, exactly.
What do you
He's already in each dimension. So I can, yeah, no, it's not T to the n.
It's beautiful that you can have the same T on the fibers as on the other polytopes. I would have thought it would have to be different scales or something.
But no, yeah. So let me say what types of, yes.
Are there any conditions about P star being rational or?
Oh, yeah. This one's, sorry. This one is rational, then this one will turn out to also be rational.
Okay.
Yeah.
sorry, but if I just take simple, stupid example of a cube, hypercube, then if I take,
But I guess I didn't tell you what P star was, but in some sense, yeah. Now I would have to tell you what, because you're gonna tell me like when I scale it, yeah, there should be a square. But so if you wanna know what P star is, let me tell you, because maybe that clarifies your question. So if P is given by this, then then P star is going to be given by okay, so it lives in n plus m, such that, so these are the equations. Okay, so when I scale it in here, that means scaling this to these vectors. And so, and so that is so, and I guess it's, and when I scale it in here, like yeah, when I want to look at this TP, that's gonna be here. So my E is 0, right, for that one. So that's like going it here, which is the same as doing it outside that one.
so it's essentially expanding only in one dimension. That's how I should interpret that?
For this one?
Yeah, because
Because
I just pull out a t to the 1, not a t to
no, because this part is actually B, remember, is a vector. Did I not write it down? Oh, I didn't write it here. B is a vector. Yeah. Okay. So as a corollary to our result, we obtain that there exists. So remember, this came from RSK, and this was the product of two Kostka numbers. So we can find some other lattice polytope such that the sum over this sum which is a weighted sum in this polytope P, that was just a simplex, is equal to the lattice points. Oh. Oops. So we get some sort of downgraded RSK. We don't know much about what this polytope looks like. It's most certainly different from this one. But yeah, it comes out, this formula comes, or the fact that we can find such a polytopal interpretation for this sum comes very quickly from our theory.
So that's k lambda mu, k lambda nu.
Yeah, I keep on forgetting to do that.
So you say that you don't know the construction of the construction?
No, we know how to do it, and with a computer and a little patience, we could give you the polytope, like, because this construction is very concrete, but we don't know like how many vertices it has. Is it combinatorially equivalent to this one? Yeah, that lots of questions we don't know about the. We think it does, but even that we're not like 100% sure. We haven't studied what our theorem outputs for this story. Okay. And I want to emphasize a few things on what type of functions we can get. And so we can get monomials by using cubes. So we can, where is it? Yeah, so by taking Q to be like some sort of cube or products of cubes with each cube depending on xi, we can get any monomial. We can also get products of this type of binomial, of this type of polynomials, because this is Ehrhart theory for the simplex. And then if you really want polynomials, well, and an arbitrary polynomial, then a single one won't work. So if you want polynomials, then you are gonna need, I mean, not necessarily, you know, like sometimes it's not like 100 necessarily, but like our theory can only tell you that the best you can do is, let me say alpha is in I, in some indexing set, then you're gonna get a collection of one polytope for each coefficient, and then in that case you're gonna have that the sum, this weighted error theory, is going to be equal to just, so yeah, this is not a very big consequence, but I would imagine you might be curious about what happens with like an arbitrary with an arbitrary polynomial. You're not gonna write it as the lattice points in a single polytope. You're gonna need one polytope for each coefficient. Okay. Okay, so so one thing that I wanted to say, okay, so I was looking at time. Yeah, let me just say a couple of things. So let me tell you another consequence of our result. Okay, so I'll call it a corollary. So we're gonna let's assume we're in part 2. Okay, so if you're in the setting of 2, then you have we have two consequences. One is that this integral can be reformulated as the volume of a weightlifting polytope. And this is just because the leading coefficient, the leading coefficient of this sum is the volume of, on the one end is the volume of this polytope, and it is known that the leading coefficient of whatever this is, so this has been studied before, and it has been used to compute integrals efficiently, and the leading coefficient of this is going to be that integral. Okay, so this immediately gives you that connection. And then the second thing is that if you want to take the maximum, so I mean, once you have the integral, you can study things like the average. What is the average of these weights over your polytope? What is the maximum? What is the minimum? So for example, for the maximum, if you care about this, you have that if, and this is going to take some effort to write down. Okay, so if this difference okay, just for time, this squiggly means just P intersects C to the N. Oops. If this difference is less than 1, then the maximum is equal to the ceiling function of that second term. Okay, and notice that, well, you could argue this looks really hard to compute, and as you increase k, this starts getting smaller and smaller and smaller. So eventually, you're going to achieve that less than 1 if your computer is fast. But it doesn't have to be a super fast computer because if you notice, this is, I mean, I guess I didn't prove it, but believe me that this falls into the context of our theorem, so you can actually find a polytope. So this is, again, counting lattice points inside a polytope, if you want to do it that way. Okay. And I think, yeah, I'm out of time. But then I'll say a couple of things that, of course, you can look at our paper. In it, we apply our theorem to just construct. We don't study these polytopes, but just from our theory, we can construct polytopes for if you care about, I'll write them down. You care about the following sums. Where this is the Littlewood-Richardson coefficients, and these are the Kostka numbers, and we can use, just because these are known to be the lattice points inside a hive polytope, these are Gelfand Tsetlin polytopes, we can, our theory gives us a polytope such that this holds, and Siri wants to say something. But we haven't studied, so if you ask me things about what holds about that polytope, good question. I hope you are interested to tell me. And also for the Newell-Littlewood coefficients. Okay, so these were studied by Shili and Gao with Gideon Orlowitz and Alex Young. And one of the things they did was actually construct a polytope such that this sum, or this number, is equal to the number of lattice points inside that polytope. And they use that to conclude things about how the complexity of computing these numbers, or deciding if they're positive or not. And so our theorem immediately gives us another polytope that accomplishes that. Again, what properties does that polytope have? We don't know, but it comes out from our theory. So that is all.